In this video, we will be discussing problems 16 through 20 on the 2023 AMC 10A that took place yesterday. So without further ado, let's get going. Problem 16. In a table tennis tournament, every participant played every other participant exactly once. Although there were twice as many right-hand players as left-hand players, the number of games won by left-handed players was 40% more than the number of games won by right-handed players. There were no ties and no ambidextrous players. What is the total number of games played? So suppose that there are two L right-hand players and L left-hand players. The right-hand players won G games, left-handers won 1.4G. Then 2.4G is the total number of games played, which is 3L choose 2, and that is 3L times 3L minus 1 over 2. So G is equal to 5L times 3L minus 1 over 8. And we want to find out what value of L makes this an integer. And L equals 2 doesn't work because that's 10 times 5 over 8, which is 50 over 8. But L equals 3 works since 3 times 3 minus 1 is 8 itself. So we can go ahead and say that this is 6, 3, then this is 8, and then G ends up being 15, and then that ends up being 21, and therefore our answer is 36. Answer choice B. Problem number 17. Let ABCD be a rectangle with AB is equal to 30 and BC is equal to 28. So let's go ahead and draw that real quick. Points P and Q lie inside BC and CD, respectively, so that all sides of ABP, PCQ, and AQDA are integers. So that's 30, that's 28, and then the side lengths of all of these are integers. We want to find out the area of APQ. So we might want to try looking for special right triangles that we can use, and that involve the length 30 or any multiple length. So the number 3 won't really work because that would mean that we'd have to have a 3, 4, 5 triangle, and that would mean that P is way over here. So that won't work. 5, 12, 13, that won't work because 30 is not a multiple of 12. And even though it's a multiple of 5, that will make it P go way over here. 8, 15, 17. 15, 30 is a multiple of 15. 30 is 2 times 15. So we could say BP is 16 and AP is 34. So that means that PC is 12. Well, now what? Well, now we want to try finding something that's PCQ that gives 12. Here it's something nice with 12. And so let's try out 16. 16 will give 14 here, and that won't work because 14 squared plus 28 squared is not a square. So what about 9? That will again give a 3, 4, 5 triangle, and that will make this 21, and we again have 3, 4, 5. So therefore, this length here is 35, and this length here is 15. So our answer is 34 plus 35 plus 15 is equal to 84. Problem number 18. A rhombic dodecahedron is a convex polygon where each of the 12 faces is a rhombus, and all the faces are congruent to each other. The number of edges that meet at the vertex is either 3 or 4, depending on the vertex. What is the number of vertices at which exactly 3 edges meet? So let's go ahead and list everything out. This seems like one of those graph theory problems in disguise. And when there's graph theory, you'll probably want to use the fact called Euler's formula, which is V minus E plus F is equal to 2. That always holds. And we are given that F is equal to 12. E is equal to 12 times 4 edges per face divided by 2, since every edge is on 2 faces. So that's 24. And because V minus E plus F equals 2, that means that V is 14. And all right, now let X be the number of vertices where exactly 3 edges meet. So I'll denote that as degree 3. Y is the number of degree 4, and that's equal to 14 minus X by the given information. And now the sum of all the degrees of all the vertices is just 2 times the number of edges because each edge is counted twice, one for each of its endpoints. So that means that 3x plus 4 times 14 minus x over 2 is equal to 24. Simplifying a bit, we get 56 minus x is equal to 48, so x is equal to 8. Answer choice D. And this should be answer choice A here. Problem 19. The line segment from A12 to B33 can be transformed to the line segment from A31 to B43, sending A to A prime and B to B prime by a rotation centered at the point P. What is the difference between S and T? So if we have points A and A, B here, and then there's A prime and B prime here, then the center of the rotation is actually the circumcenter of the cyclic quadrilateral AB A prime B prime, which is just the intersection of the perpendicular bisectors. So we just need to find out the perpendicular bisectors of AA prime and BB prime, and we'll be set. So let's deal with AA prime first. The midpoint of, so that we have 1, 2, and 3, 1. The midpoint is 2, 3 halves. And the slope is 1 minus 2 over 3 minus 1, which is negative 1 half. So y is equal to 2x plus something. And since 2 times 2 minus 5 halves is equal to 3 halves, the perpendicular bisector is y is equal to 2x minus 5 halves. All right, now let's focus on BB prime. That has the lengths 3, 3, and 4, 3. And because they have the same y coordinate, it shouldn't really come as a surprise that the perpendicular bisector is x is 3.5 is equal to 7 halves. And then if we plug that into here, we get y is equal to 7 minus 5 halves is equal to 9 halves. So therefore, our center of rotation is 7 halves, 9 halves, and that means that it's 1. And that's answer choice C. All right, problem number 20. Each square in a 3x3 grid of squares is colored red, white, blue, or green, such that every 2x2 square contains 1 square of each color. And one such coloring is shown there. So now we have our 3x3 grid, and we want to find out how many colorings are possible. So let's go ahead and see what happens if we try labeling the top square in the left. We could get to something from there. Let this color be 1, 2, 3, and 4, suppose. Then these two colors in some order must be 2 and 3. So there are two cases. One is where this is 2 and 3. Then that means that these two must be 2 and 4 in some order, and these must be 3 and 4 in some order. So that becomes 4, because both must have 4. And if 4 was here and 4 was here, then they'd have a common one, and that would not be good. And then that would mean that 2's here and 3's here. So that's one ordering. So that's 1 plus, all right. And now let's go ahead and go to the second way that this is possible, for this is 3, 2, and 3, 2. Then we must have 3 and 4, and then 3 and 4. Or, yeah, 3 and 4 and 3 and 4. So the first case is that 3 is in the middle, then this is 4, 3, and 4. So that's one case. And then the second case is where it's 3, 4, and 3. So there. And then we must multiply by 4 factorial, since there are 4 ways to arrange 1, 2, 3, and 4. And that gives the answer 72, which is D. So thank you so much for watching this recap of the problems 16 through 20 on the 2023 AMC 10A. Please subscribe if you want to see more videos.